All right, so Foundations of Math 10, this is 5.6 in your, what is this? Pearson Foundations and Pre-Cal Math 10 textbook. So page 300 is where we're at, if you're following along. Now this is a chart that's on page 300, and you can jot this down or you can just follow along. So I want to explain to you a few key characteristics of linear relations and what the graphs look like, what the table of values look like, and so on. So, first of all, let's note that when we're talking about linear relations, notice that the root of this line, this word linear, is line, and so it forms a straight line. So we have a relationship that is linear, means that the graph is a straight line. Now here we have individual points, and you'll see on this graph, individual points. It's not a connected line. So not all relations have to be connected. And I think we talked about this already, that sometimes it's appropriate to connect the lines when the points in between two plotted points make sense. For this case, this looks like it's a case of cost of pizza where that's related to the number of toppings, okay? So you can only have whole numbers of toppings. You can have 0 toppings. You can have 1, 2, 3, 4. You can't have 1.7759 toppings, right? That's why there's no point at 1.7795 right here. There's no point there, and because it's not reasonable, all right? So that's why we just have individual points. Now, properties of linear relations are that the points or the line itself that's graphed is a straight line. Now, these points are all in a straight line. If you look at this carefully, they all would form a straight line if you were to connect them, okay? Over here is the table of values. So the number of extra toppings, okay, so we have 0, 1, 2, 3, 4, and 5. And in a table of values, this would be the independent variable. I'll talk a little bit more about this and we'll label this a little bit later. But this is the independent variable, independent. Because this is the one that you kind of start with independently at the beginning. You start with this information, and then you can determine what the cost is. See, the cost is dependent upon the number of toppings. So that's why we call this the dependent variable. The independent variable is always on the bottom. That's the horizontal, so the x. And the dependent variable is always in the vertical, the y. Okay? So this is like x and y here. Got it? Table of values, that's what this is called. So we always put the points or the values that are connected to each other in the same row. So 0 goes with $12. 0 toppings, $12. That's kind of your base price of the pizza, I guess. This topping, 1 topping, the total cost would be $12.75. Now you could do a quick calculation right now, and you've gone up 1 topping, and you've gone up how much in cost? Yeah, 0.75. Okay. All right, that's cool. If we do this over and over again, what we would see is that we would be adding 1 to each one of these, right? Adding 1 topping. 5 toppings. I'm not sure who orders a pizza with 5 toppings. That sounds pretty good, actually. Mine would be sausage, pepperoni, ham, more meat, and more meat. But, you know, to each his own. Maybe some mushrooms in there, maybe some green peppers, maybe some olives, black olives, maybe some anchovies, tiny little fish. Come on. All right. Well, we all have differences of opinion. No pineapple, no fruit whatsoever, except for tomato. Tomato is technically fruit. Did you know that? So that's the only fruit I like on pizza. Tomato paste. Okay, that's it. No other pineapple. Sorry.
Why?
Sorry if you're from Hawaii. I don't like Hawaiian pizza.
It was made in Ottawa.
Wait, what?
Yes.
You're in Ottawa? What'd you say? Ottawa?
Oh, is
Hawaiian pizza was made in
is
Ottawa.
it just called Hawaiian because
Because it was found
Pineapple.
in the box of, because the box of
Oh boy.
the pineapple itself said Hawaiian on it, so it's named after Hawaii.
Okay.
No, I think
that's an urban legend. I think that's a lie from the pit. Anyways, let's keep going. Watch this. Each topping, as it's added, adds what? It does. This also adds 75 cents each time. Okay? My 75s are getting weirder and weirder as we go down. But you get the picture, right? So watch this. In a linear relation, when you look at the chart, if this goes up by a consistent amount and the corresponding partners to these points also go up by a consistent amount, then, I missed one there, it looks like, 75, 75, Okay, I missed one. Anyways, they all go up by 0.75. Then you have a linear relation. Because watch this. As this increases by 1, this goes up by 75 cents. As this increases by exactly 1, the price goes up by 75. So notice that each horizontal and vertical change are identical, and that's what forms a straight line when you were to connect those points. And this is not a straight line that I just did there, because it's tough to do on this tablet. Anyways, you get the picture, okay? So this is what you're looking for when you have a table of values, and when you have a graph, you're looking for points or a line. That's a straight line, okay? If the points were to go like this, okay, which could be the fact, because, you know, the pizza company might start losing money if you, anything over like 3 toppings, they might start losing money. That's like, okay, well, I have to charge more because that's actually a lot more product I'm spending, and now I'm starting to lose money. If someone ordered 10 toppings, that would cost me a lot more than, you know, $7.50, let's say, right? 10 times 0.75. So they might not have a linear relation here. This particular pizza joint does. And it's a straight line, okay? So each topping is 75 cents. Now we can learn a lot from that, right? You've heard of this word before, right? Slope. Have you heard of slope before, right here? You heard of this term before? Oh my, disappeared. Okay, there's the homework if you're in calculus. Okay. Technology. Reload, please, whatever. Ugh. Okay, slope is rise over run. So notice that the rise is 0.75 for each run of 1. So the rise is 0.75, the run is 1. So the slope here for this particular situation is $0.75 over 1 topping. Okay? Or the rate of change is the same as the slope. Slope rate of change is $0.75 per topping. Okay, does that make sense?
Yeah.
Okay, good. Makes sense to one person. Anybody else? Nod, yes, good. 5 out of 5, all right. Okay, all right, so that's good. We've learned some good stuff there. So let's review. The slope is like the blank of a line. What word am I thinking of that I want to put in there? It's the what? It's another way to put it. It's the value of the slope is the, what were some of the words you were guessing? Angle? Right idea, but you probably won't be able to guess this one. Is the steepness of the line. Steepness. I knew you weren't going to guess that. I don't even know if it's a real word. But I'm using it, so it's a real word here in this class, okay? The steepness of a line. So if you have a larger value slope, then you have a steeper line, larger value slope. And if the slope is 0, that means there's no steepness, it's flat. Okay? Now, it is also the rate of change of one variable compared to the other. So slope can be thought of as the steepness of the line, or more specifically, the rate of change of one variable compared to the other. Just like the toppings on the pizzas. The slope is the rate of change. Okay? Here it is right here. Every new topping is $0.75 or 75 cents. So that's the slope, 0.75. Okay? Now on the graph, is everyone okay there? Any questions about those last 2 statements? Okay. The slope, now how do we interpret that from the graph? So it is the slope also equals the change in 2 y values divided by the change in the 2 corresponding x values. Okay? So how do you calculate the slope? The change in 2 y values, any 2 y values that you would see on the graph. So the vertical change in 2 y values divided by the change in their corresponding x values, which is rise over run, which we just talked about. Also can be written this way. Now notice I have on the graph here And I don't know if you've ever seen this before. Have you ever seen this symbol right here? A little triangle. Have you ever seen that? No? Yes? No? Some of you are nodding, some of you are kind of unsure. So this is the Greek letter delta. Okay? It's like the Greek letter D. Okay, we have D like this. They have D like this. Triangle. Okay? Pretty close. But it's delta. And in math and science, it means change in. So change in y divided by change in, why am I writing y again? X. Change in y divided by change in x. That's how we find the slope. And of course, we have to use the 2 points, so the y values from the 2 points divided by the x values, the difference in x values for the 2 points. So rise over run. Rise, change in y, run, change in x. Rise, run. Okay? Rise, run. The next time you guys have a coffee house and you want to do some line dancing, I want to see the slope line dance, okay? Rise, run, rise, run. Hey, rise, run. Turn sideways and click your heels, okay? All right. Just an idea. Just an idea. Just a thought. If I come, I will teach you all that one, okay? We'll do some math line dancing, even though I'm horrible at line dancing. I'm horrible at any dancing. I don't dance. Honestly, if I really wanted to dance, I would just pretend a bee is trying to sting me. That's my dancing. A bee is trying to sting me. That works for me. People are like, wow, that guy's innovative. No, just pretending a bee is stinging me and I'm trying to get away from it. All right. Back to focus here. Back to focus. All right, here's an example from the textbook. Okay. This example says, and you don't have to write this down if you don't want to. Okay. Just watch, because it's just confirming kind of what we've been talking about here. So the cost for a car rental is $60 plus $20 for every 100 kilometers that's driven. Okay, so we have a flat rate of $60, and then we have a rate. Notice I said rate. A rate of $20 per 100 kilometers. Okay, so every 100 kilometers that's gone, we go up $20. Every 100 kilometers that's gone, we go up $20. What does that look like in the chart? Well, if we were to take any two corresponding quantities from those, distance and cost, at 0 kilometers driven, you owe $60. That's the flat rate. If you go 100 kilometers, okay, as soon as you click to 100 kilometers, you now owe $20 more, 80. 200, 100. Notice that we're adding 100 each time, and we're adding 20 each time. If these are consistent throughout all of the points that are written there, you can be sure that this is a linear relation. From what you're given, this looks like a linear relation. Now, a nonlinear relation would mean that as you drive further, let's say, it would go up by more. See, something like that. If this was the case, guess what? This is not a linear relation. Okay, if they're going up by differing amounts, that's not a linear relation. That would be the case where you have something like this. It would like grow exponentially a little bit, or at least it would be a curve. It would not be a straight line. Okay? Okay, that's what that would look like. So beware. Make sure you can check. The independent variable would be the distance driven, because that's kind of what you remember start with. Okay? So if you're calculating your cost, I want to know how much I'm paying, so what does it depend upon? What does the cost depend upon? Well, it depends on how far I drive. So how far you drive is the independent variable. The cost is the dependent variable. Hopefully that's understood. So for a linear relation, a constant change in the independent variable, right here, must result in a constant change in the dependent variable. If that does not match up, you do not have a linear relation. Okay? Out of 5? 1, don't get it. 5, get it, it's good. Or give me a thumbs up. I'll assume that that's good too. Or you have to go to the bathroom, one of the two. Remember that symbol for having to go to the bathroom? I missed that. Yeah, we used to do that. Not now, Sally. You have to stay here. Okay? Okay. Any questions so far? Any questions so far? All right. Let's get some practice with graphing a line, okay? This is really important. You should know how to do this, but I find that in high school, students are not very good at graphing lines, especially from going just from a table of values. So I want you to write this down so you have this, and you can do this with me. So we're going to graph this line right here, and the line is, let me just move this over. Graph this line right here. The line is y equals 2x plus 5. This is a straight line. We're going to see that it's a straight line. And then we're going to examine this form of a straight line towards the end of class. So graph this line right here, y equals 2x plus 5. And I've got a coordinate plane. Okay, right. Pencil, paper, contacts, move it around. Yeah, here we go. Open up your books, right? Everything. Oh boy. Okay, so the line is y equals 2x plus 5. And I know that this is a straight line. You might know this is a straight line. We're going to prove this is a straight line by generating a table of values over here on the right. Okay, so a table of values is when you have a 2-column table, okay, and usually the first column is x, the second column is y. And the x is the independent variable, the y is the dependent. And in generating a table of values for any kind of relation or any kind of equation, you randomly pick, if it's not told what x values you should pick, you can randomly pick some numbers for the x. You choose those first. And then I'm going to choose some negative and some positive values near 0. So I'm going to go -3 as an x value. I'm going to randomly choose that. Now, the meaning of this independent variable means that I can now plug it in to where I see the x, and I can solve for y. So it's actually going to look like this, right? This is how you figure out what the y value is. You plug your -3 in where the x is. This is a 2 times x, so this is a 2 times -3. That's -6 plus 5. Y then is -1. So I put it right here on the chart there, on the table of values. So that point is -3. I go -3. Sorry, I go -3 in the x direction, and I go up 1 unit. Now I'm going to say this is 1 unit. 1 unit right here. Okay. -3. Oh, down 1 unit. Sorry. Where's my 5? So this is -5. I'm working on the scale here. You're right. I got to go down. So, I erased my whole graph. Okay, there we go. So -1, -3, -1. So the point is roughly about here. Okay, so this is the point -3, -1, right there. Everybody see it? Tough to see when I have that big -3 there, but I'll put -3 up there. Okay, so that's it right there. All right, so let's pick another one. Let's go -2. Okay, so -2. I'm going to substitute -2 in there, and I'm going to have -4 plus 5, and that's going to be +1. So -2, +1. Okay. Now, it'd be good to stretch this graph out a little bit, so I'd be a little more accurate with my lines here, but we're doing our best we can. All right, so let's go, let's skip -1. Let's do 0. So if I put 0 in, 0, I've got 0 plus 5, or 5. So I have the point 0, 5. You guys kind of getting the pattern here? So 0, 5, okay. And we do some more. Let's do a couple more. Let's do +1. So 1, that's going to be 2 times 1 is 2 plus 5 is 7. So 1, 7. So 1, 7's about here, let's say. And then if I go 3, so 3, 2 times 3 is 6, plus 5 is 11. So it should be 11. So 3 and 11. So I go up to about 11 here. Maybe around there somewhere. All right, so if we put all this together, and again, I apologize that this is not exactly, the most accurately placed points. I don't have any lines on my paper here, but if I make a straight line, and if I were to connect these points, it would look something like this. Let's just see how well we did here. Oh, not too bad. Not too bad. Not too bad at all. Okay. So we've got, well, I'll maybe try and adjust this just a little bit. It's tough to do. Okay. All right. So these points, if plotted, perfectly on some nice lined paper, then we would have a straight line. They would all fall into a straight line. Okay? Now, what should 2 be if I were to put 2? What do you think 2 should be? It's somewhere between 7 and 11. So what would 2 be? Should be somewhere around here, which would be just under 10, looks like. So 2 times 2 is 4, plus 5 is 9. That's exactly what it looks like right here. Okay? 9. All right. Everyone see how to graph the line, how to choose some point values of x, plug it in, plot your points. Okay? All right. So that's what the line would be if all the dots were connected. It's a straight line. Okay, let's talk about slopes a little bit here. So you might know this, you might not. If the slope of a line rises from left to right, okay, so you have a line that is indefinite in both directions, but it has a slight rise from left to right, it has a rise, left to right. This is a positive slope, okay? A positive slope has a rise from left to right, so it looks kind of like this. Slanted, goes up from left to right, okay? It's a rise from left to right. Inwards. A negative slope, okay, negative, from left to right, the slope goes down. So there's a drop from left to right, okay? I'll call it a drop from left to right. And so the slope that would be associated with that would be negative. Now think back to our pizza example, right? As we increase the number of toppings, the price goes up. That's a positive slope. It was positive $0.75, right? Now, let's say that's the more toppings you choose, the price of the pizza goes down. That would be a poor decision on the pizza place, but then every new topping drops the price. So that's a negative rate of change, you see? Negative slope. Okay, we wouldn't want to do that. If you start a pizza joint, please don't do that. You will go bankrupt. Zero slope, okay, is a flat line. It's a flat line. A flat line. Okay? Because, well, if you think about what slope is, right? Slope is rise over run. So from any 2 points on a horizontal line, what is the rise between those 2 points? Like how far up or down do you have to go to get to the next point? 0, right? They're on the same horizontal point. So you have 0 divided by the run. 0 divided by any number other than 0 is just 0. So we have a 0 rise, that's therefore a 0 slope. Now, the problem comes when we have a vertical line. That's a problem. This slope is undefined. Why? Because we would have a rise, a given rise, but then we would be dividing by a run of 0. So dividing by 0 is a problem. So a vertical line is undefined slope. Okay, so that's for a vertical line. All right, you understand that? The slopes there, you get that? Positive, negative, 0, undefined? Okay. Okay, pretty important stuff. There's a lot of information today. I get it. You guys are doing great. I do want to talk about y equals mx plus b, though. This is a form of a line. Have you ever heard about y equals mx plus b? You remember in grade 9 doing this? Okay. So this is the slope y-intercept form, right? You'll see this in science and math and everything. Very common. It's a very common way to express a linear relation or a linear function. We talked about functions the last couple sections, right? So a straight line, linear equation, is a linear relation. It's also a function. A straight line is also a function, as long as the slope is not undefined. So you can't have infinity times x, okay? That doesn't count. But everything else, any other number for m, any other number, positive, negative, small, large, decimal, fraction, irrational, rational, is a function, okay? So from here, the reason why this is called slope y-intercept is that the m represents the slope of the line, always. Slope. And the b represents what? Yeah, it's a constant. The other part of this, name of this, the y-intercept. Yeah, the y-intercept. Okay. Yeah. Now, from our last example, I'll just go back there real quick. I will come back to this in case you haven't finished writing that down. But look at this last example. Y equals 2x plus 5. What is the slope between any 2 points? If you want to calculate the slope between any 2 points, well, from 0 from 5 to 7. You see, we went from 5 to 7. That's 2. And this is 1. So the slope here is 2 divided by 1. Look at that. We have a 2 multiplied by the x. What's the y-intercept? Well, the y-intercept is where the graph contacts the y-axis, and that's right here at y equals 5. Look at that. There's your y-intercept. Okay? So this is in y equals mx plus b form, and the m is the slope, and the b is the y-intercept. So just as an example, if you see an equation written like this, where, you know, the cost of something is determined by the distance that you travel or whatever, and I think this was the example we used about the car, right? $60 is the initial amount that you would be charged for renting a car, and then you would be charged $20 per 100 kilometers, which actually reduces to what? 2 over 10, or 0.2. So that is the slope, okay? The rate of change in simplified form. So you have your slope of the line right here. You have your y-intercept. The y-intercept is the initial amount that you would pay right here, 60, and then it would go up, you know, $0.2 per kilometer, or $20 for every 100 kilometers. And that's your rate of change. So this is the independent variable, the distance that you travel, and the cost is the dependent variable. Remember, cost depends upon the distance you travel. So this is also y equals mx plus b. Y, your cost, that's the vertical axis. Y equals m, your rate of change, the slope. X, which is the horizontal axis, the distance, plus b, your intercept right here, 60. Okay? So is this pretty easy? You guys putting this together? Yeah? Feeling okay about it? Okay. So just a quick check here. I want to see if you know what you're doing. So do both of these represent linear relations or not? Let's just check. The difference between these is this plus 5, this is plus 5, okay, 5 and 5, right? This is what? That's 9. This is 9. This is 9. This is 9, okay? So does this look like a linear relation to you? Yeah, it does. So linear, okay? Now this is going up 5, 5, 5, 5, so plus 5 over here. This is going plus 75. This is going plus, whoops, 225 plus, whoa, 375. So right away you see that these numbers are different. So this is not a linear relation, okay? For every increase, the same increase on the x-axis like this, the values are going up higher, right? So they are not a straight line. It's curved. Okay. All right. Here's your assignment. 5.6, number 3 to 6, 9, and 15. Please jot that down. And I'm going to let you start that assignment. So let's check the website, mrmathwell.com, where you go for all of your math and science needs. And loading. Here we go. It's the textbook we're using. And look at this all the way down to chapter 5. So what do we have, 5.6? Ooh, okay. So this is, did I have this choice in here? I need to have that choice in there. So 3 to 6, 7, 9, and 15. 3 to 6, 7, 9, and 15. So add the 7 here. I'll put it up here.
3 to, wait, why not 3 to 7?
Yeah, sure. Because I added 7 later. See? So 3 to 7 is fine. And then 18 to 22. So I'm going to give you some time tomorrow to work on this as well. So I just have a little bit of a different assignment than the original, I guess. That's also really small. Let me make that bigger for you. So choose one from 18 to 22. Now, if you have time for this, I'm making this optional. So this is word problem. I would like you to think through this. Every one of you should try this. Okay? But when you're done, these required core questions right here, then I want you to choose one from 18 to 22. Okay, so shortened class today. You don't have a lot of time to work on this, but I want you to get started, see if you can get 1 or 2 questions done before the bell rings. Any final questions? All right, 1 bar. Killing a beat.